In this lecture, we'll go through method of images. For that discussion, you need some initial knowledge on conductors in electric field. So we'll first discuss what will happen to conductors when those conductors are placed in an electric field. We can divide materials based on the electrical conductivity into mainly three types. So we have insulators. So in insulators, almost all the electrons are attached to the atoms. So insulators don't have much electrical conductivity because electrons cannot move freely in an insulator. Then we have semiconductors. So in a semiconductor, with providing some energy, we can make the electrons move. So there are like little bit of free electrons there, but if we want to have a good conductivity there, then we need to provide some energy to these semiconductors. Then we have conductors. So in conductors, we have one or more electrons per atom that are free to roam. So in insulators, there is no much electrical conductivity, but in conductors, we have free electrons, at least one or more electrons per atom are free to roam. Therefore, we have some good conductivity in these conductors. Now, if I place the conductor in an electric field, so let's say there is an external electric field E0. With this provided external electric field, since there are one or more electrons per atom that are free to roam, what will happen to the electrons inside this conductor? Electrons will move to this side with the provided electric field directed in this direction. So once we have electrons move into this direction, there will be a positive charge in this side of the conductor. Now, with the provided external electric field, electrons move like this. Therefore, we have a charge separation like this now inside the conductor. Therefore, we can say there is an electric field in this direction, E1, inside the conductor. Now, we have, if we take the total electric fields, we have E1 in this direction and E0 in this direction. So, because of this E0, this E1 resulted. So until the electric field is balanced, there will be charges, mainly electrons, moving inside the conductor to occur this E1 electric field. Because of that, approximately or mostly this E1 and E0 direction is opposite and the magnitudes will be same. Therefore, inside the conductor, electric field will be 0. So considering conductors, the first thing we learn is electric field is 0 inside the conductor. Now, once the electric field is 0, we know that divergence of electric field is equal to rho over epsilon naught. So if E is 0, then rho should be also 0. So rho is 0 means, so there are charges inside this conductor, but rho is equal to 0 means in this situation is, now with the positive and negative charges inside, the net charge density inside the interior is 0. There are charges, but the net charge is going to be 0. So positive and negative are going to be balanced. Therefore, net charge density inside this conductor is going to be 0. And the excess charges are on the surface of the conductor. So the second point, net charge density in interior is 0. There are charges, but those charges are balanced with positive and negative. Therefore, net charge density is 0. What else? Also, from this discussion, we discussed that third point. So if there is any excess charge, so these electrons move to the surface and we have positive charge here. Therefore, these charges on the conductor, these excess charges on a conductor those charges will reside on surface of the conductor. So these charges, once these charges move, those charges on the conductor resides on the surface of the conductor. So these electrons are on the surface here, and because of those electrons move to the surface here, excess positive charge will be on the surface here. Okay, and also conductor is a equipotential surface. So which means we can move charges freely on the surface of the conductor. Okay. And then, so once these charges move to the surface, electric field generated by these charges, those are moved to the surface. So that electric field is perpendicular to the surface just outside the conductor. Okay. Now, because of this reason, can you remember if we have two like radius situations like this? Now, there are charges here and charges here. So, since electric field is perpendicular to the surface just outside the conductor, we will have a high charge density here and low charge density in the regions where we have high radius. Therefore, in situation like this, we will have a large number of electric field lines when the radius is low, and electric field lines in the regions where the radius is high will be low. So when the radius is low, there will be large number of electric field lines. But when the radius is high, the number of electric field lines will be low. Okay. So that is some basic summary about conductors. When we place these conductors in an electric field, there will be an electric field generated inside the conductor. Therefore, when we take the total electric field inside and the external, the net electric field is going to be 0 inside the conductor. And then since the electric field is 0, rho is also 0. So there are charges inside the conductor, but the positive and negative will be summed up. Therefore, the net charge density inside the conductor is 0. And charges on a conductor, if there is any excess charge, then those charges are going to reside on the surface once we place this conductor in electric field. And also a conductor is an equipotential surface. So conductor is an equipotential. We can move charges freely on the surface of the conductor. Then because of the movement of these charges to the surface, the electric field generated by these charges on the surface is perpendicular to the surface just outside the conductor. And if the radius is low in a certain geometry of a conductor, then there will be large number of electric field lines there. And if the radius is high, then the electric field lines that are occurred from those geometries are going to be relatively low. Okay. Now, this information is required for our discussion today. So, have you done taking notes out of this? Do you want more time to take notes out of this? Okay. Now, let's say we have a conductor and there are some positive charges here. And I want you to calculate the electric field just outside this conductor surface. So try to calculate that one. So I have a conductor and there are some positive charges here, negative charges, let's say negative charges are here. So I want you to calculate, because of these positive charges, what is the electric field just outside the conductor. Try that one. So what can we do here? We can use the Gauss law. E dot ds is equal to Q over epsilon naught. So let's say the charge density on this surface is sigma. Charge density is sigma. And what kind of a Gaussian surface I can consider in this situation? So I will consider a cylindrical Gaussian surface covering this just outside the surface. So now we know electric field lines are perpendicular to the surface and there are no electric field inside the conductor. Therefore, electric fields will not be here. Those will be cancelled out. And if I say the area of this surface is A, then magnitude of the electric field, so E dot ds, surface integration, surface area is A, is equal to, now the charge density is sigma, therefore total charges covered by this Gaussian surface will be sigma times A over epsilon naught. So area cancels out. Then we have magnitude of the electric field there is equal to sigma over epsilon naught. And if I say direction here is x, then electric field. So if the surface is perpendicular to the direction x, then the total electric field is equal to sigma over epsilon naught, the direction of I. Okay. So that is the electric field just outside the surface of this conductor because of the excess charges, excess positive charges here. Then we know the relationship between electric potential and electric field. So electric field is equal to minus gradient of electric potential. Now we know the electric field here. So it is sigma over epsilon naught, direction I, is equal to, now this del operator, this dabba over dabba x I plus dabba over dabba y j plus dabba over dabba z k, and we have the potential, this scalar function v v v. Now, if we look into these two sides, here we have direction in I and we have I, j, and k. But since we don't have any components of j and k, we only have this I component. We only need to consider this I component. Then sigma over epsilon naught is equal to minus dabba v over dabba x. So using this relationship, if we know the charge density, then we can calculate the electric potential. Also, if we know the electric potential, then we can calculate the charge density, vice versa. So we can write charge density is equal to minus epsilon naught dabba v over dabba x. So x is the normal direction to the surface of this conductor. Okay, so we can calculate the electric field, and then using this relationship, we can calculate the charge density. And also now we have a relationship between electric field, charge density, and electric potential. Okay. Now we need this information for the question, a specific question that we are going to discuss today. Now, the main question is, so we will have a point charge. So have you done taking notes out of this? Do you need more time to take notes out of this? So what we are going to discuss today is, suppose a point charge. So we have a point charge Q is held at a distance d above an infinite grounded conducting plane. So we have a conducting plane and it is grounded. Grounded means potential on this conducting plane is 0, and this charge is held at a distance d. So now the question is, what is the potential in the region above the plane z greater than 0? So let's say this direction is z. So if I take a certain point like this, x, y, and z. So in a region where z is greater than 0, what is the potential? So if I consider a point like this, what is the potential here? Now, how can we calculate the potential at this point? So let's say this point is P. At this point P, what is the potential? So here I have a point charge, and at this point we need to calculate the potential. So can we just consider the separation from this point to this point and then calculate the potential? And what is the influence from this grounded conducting plane? What is the significance of this grounded conducting plane? What do you think? Now, with what we learned regarding the conductors, someone please tell me your ideas. Anyone, if you have any idea, what will happen if I bring a certain charge Q here? What will happen to the charge distribution on this grounded conducting plane? මේ විදිහට charge Q කියන එක මේ conducting plane grounded conducting plane එක ළඟට ගෙනාවහම මේ conductor එකේ තියෙන charge distribution එකට මොකක් වෙයිද? ඔයගොල්ලෝ හිතලා කියන්න බලන්න. So think, when I bring a certain positive charge here with Q, now we have a conductor here, and in a conductor, those excess charges can move freely. So what will happen to the charge distribution on this conductor plane? What do you think? So I have a positive charge here. Then we have free electrons in this plane. On this conductor, we have free electrons. So what will happen to those free electrons? Will those be uniformly distributed? Will those be gathered to a certain location? What will happen? So because of this positive charge will induce a certain amount of negative charge on the nearby surface of the conductor. So because we have the positive charge here, a certain amount of negative charges will be induced from this conducting plane because we have free electrons here. So we cannot just calculate the potential by considering the distance here and the charge here. So if I just consider the distance here and the charge, then the potential will be 1 over epsilon 1 over 4 pi epsilon naught q over r, if r is the distance from this point to this point P. But since this conducting plane will induce a certain amount of negative charge, we cannot directly calculate the potential by looking into this equation. Okay. So now in a situation like this, the total potential is due in part to charge Q directly. There is a potential influence for the potential from this charge Q, and also the potential will depend on the induced charge on this conductor surface. Okay. And it is hard to calculate the potential since we don't know how much charge is induced and how it is distributed. So we don't know how much of charge is induced on this conductor plane and how it is distributed. So to solve this question, now we need to calculate the potential in the region above this conductor plane. We are going to do a little bit calculation, and it is not directly this situation, but the calculation that we are going to discuss, we can show that the calculation we'll do, it is similar to this situation. Okay. So we are going to do a certain calculation, and we can show that the calculation gives the same result as this situation where we have a conducting plane and a charge outside the conductor. Now, the calculation we are going to do, this technique is called the method of images. The technique that we are going to do is called the method of images. Now, what we are going to do is, now you will have to keep in mind the question that we are discussing, but we are going to do a certain calculation. The technique that we are going to discuss is the method of images, and we can show that the results that we are getting from this method of images is similar, is the same as this situation. Okay. Now, what is this method of images is, so we have I'll follow this image. So we have y direction here, and we have z direction here, and we have point charge q here with a distance d. Then we need to calculate the potential at a point P. Let's say the coordinates here are x, y, and z. Then what I'm going to do is, since I have a positive charge q here, I will introduce a new charge with the same magnitude, same amount of charge, but opposite in sign. So here I have a positive q, but I will introduce a negative q charge here. Okay. Then let's calculate the potential at this point P due to both of these charges. Also, the distance, if this positive charge is located at a distance d above this xy plane, then the negative q charge is located with a distance d from the xy plane. So let's say the vector here is r from this point to this point P. Then the vector here is r prime from this point to point P. And we have r naught vector from origin to point P. So we will calculate now we are going to calculate the potential at this point P due to this positive charge Q and negative Q. So potential at point P due to plus Q, and potential at point P due to minus Q. So obtain equations for these two conditions: potential at point P due to this plus Q and potential at point P due to this minus Q. So obtain values for these two situations. Try that one. So we can calculate the potential 1 over 4 pi epsilon naught, then charge over separation from the location of the charge to the location that we are interested. And the location that we are interested have the coordinates x, y, and z. So this distance, it is z, and distance from the point we are interested to this point, it will be z minus d. So you know how to calculate the magnitude of a vector, and So calculate these two for the potential at point P due to plus Q and potential at point P due to minus Q. So we have 1045 epsilon naught. Charge here is Q and the separation. Now we need to consider from this point to this point, vector is R. The magnitude of that vector, x coordinates and y coordinates are just x and y, but now the z coordinate is z minus d. Therefore, we have x squared plus y squared plus z minus d squared square root. Then potential at point P due to minus Q. So we need to consider this R prime vector. So x and y are just x and y, but for z, for this vector, we have from here to here, it is z plus d. So the potential at point P due to minus Q, it is 1 over 4 pi epsilon naught. Now we have minus Q over x squared plus y squared plus z plus d squared square root. Okay. So from here to here for this r vector, we need to consider z minus d. From here to here, z vector, it is z plus this distance, d distance. Okay. Then what is the total potential due to both of these charges? It is equal to the summation of these two values. So we have 1 over 4 pi epsilon naught q over x squared plus y squared plus z minus d squared square root. Then here it is minus q over x squared plus y squared plus z plus d squared square root. So this is the total potential due to this plus q, which we had initially. Then I introduced this negative q. I introduced this one. So the potential at this point P, because of this q and negative q, this is the total potential. And from our previous discussion, we obtained the relationships between the electric field and the charge density and also the electric potential if I have a conducting plane. Now let's say this xy plane is a conducting plane. Now let's say this xy plane is a conducting plane and we will calculate what is the potential. Now we know, like with this situation, we know what is the potential. And if I consider this xy plane to be a conducting plane, let's calculate what is the charge density. So if xy plane is a conducting plane, what is the charge density due to this calculated total potential? So what is the charge density due to this calculated potential that is resulted because of the plus q and minus q? So to calculate that one, we can use this equation. Charge density is equal to minus epsilon naught times gamma v over gamma x. So x in that previous situation, x is the direction normal to the conducting plane. In here, the direction normal to the conducting plane is z. So we have charge density is equal to minus epsilon naught gamma v over. Now in this situation, direction normal to the conducting plane that we assumed xy is a conducting plane is z. So the direction normal to the conducting plane is z, gamma z. And then we can calculate the charge density due to this potential here. So sigma is equal to minus epsilon naught. So since we only have one direction, z direction, we can consider it has an ordinary differential equation d over dz 1 over 4 pi epsilon naught. Now the total potential V, this one, Q over x squared plus y squared plus z minus d squared square root minus Q over x squared plus y squared plus z plus d squared square root. So calculate the charge density by doing this differentiation. Try this one. So we have minus epsilon naught and 1 over 4 pi epsilon naught is a constant. So we can take it out. And Q is also a constant. And here, so 1 over square root, and we have z minus d to the power 2, and so we have minus half times x squared plus y squared plus z minus d squared to the power 3 over 2, and when we differentiate z minus d to the power 2, we have 2 z minus d, and here also we are going to get minus half one over x squared plus y squared plus z plus d squared to the power 3 over 2 times 2 times z plus d. Then when we simplify this one, we should get minus epsilon naught cancels out, minus z minus d x squared plus y squared plus z minus d squared to the power 3 over 2. So we have q and 4 5 epsilon naught cancels out, minus minus it will be plus z plus d over x squared plus y squared plus z plus d squared to the power 3 over 2. So this is the charge density, and so this charge density is only going to reside on the xy plane. So xy plane means z is equal to 0. So our assumption is xy plane is a conducting plane. So xy plane means z is equal to 0. Therefore, the charge density on this plane, we need to consider z is equal to 0. So when z is equal to 0, now the charge density is equal to minus q over 4 5. Z is 0, Z is 0, here is also 0, here is also 0. So we have d plus d here. Then we have x squared plus y squared plus d squared square root. Sorry, d squared to the power 3 over 2. Then charge density is equal to minus q d over, so 2d 4 2 4, here we have 2 5 x squared plus y squared plus d squared to the power 3 over 2. Now, when we look into this result that we obtained, we assume that xy plane is a conducting plane, and we obtained the charge density due to these two charges plus q and minus q. So what will happen if we increase the distance d? If we increase the distance d and if I reduce the distance d, what will happen? And also this charge density, charge distribution is depending on x and y. So then let's see what is the total amount of charge that is generated from this charge density. So if I know the charge density, then to calculate the total charge Q, what we can do is we can integrate this charge density with the area that we are considering. So if this, here we consider xy plane is a conducting plane, so x should go from minus infinity to plus infinity. Y should also go from minus infinity to plus infinity. or we can change the coordinate system to calculate the charge density. So try this one. Try to calculate the total charge due to this charge density on this total XY plane. So we assume XY plane is a conducting plane. Try to do this calculation. Now we need to calculate the total charge due to this on the XY plane due to this charge density. So I'm going to change the coordinate system to plane polar coordinates. So on plane polar coordinates, we have, so since we are considering XY plane, we have the distance R and angle theta. So R should go from 0 to infinity and theta should go from 0 to 2 pi. And R is equal to x squared plus y squared. R squared is equal to x squared plus y squared. So we have minus qd are constants and 2 pi is a constant. 1 over r squared plus d squared. And in this coordinate system, we need to select the, for the area integration, it is r dr d theta. And r is going from 0 to infinity. So we have minus qd over 2 phi angle is going from 0 to 2 phi, and we don't have any dependence of this theta in this term, so d theta. Then r is going from 0 to infinity, r squared plus d squared d r. So it is equal to minus q d over 2 phi. So here it is like 1, and when we integrate 1, we will have theta. So theta is limits are from 0 to 2 pi. So here we are going to do 2 pi, and we need to integrate 0 to infinity r over r squared plus d squared d r. So here it's x squared plus y squared plus d squared to the power 3 over 2. So we should also have that here 3 over 2. Power is 3 over 2, 3 over 2, 3 over 2. Try this integration. Limits are from 0 to infinity r over d squared plus r squared to the power 3 over 2 dr. If you got the answer, please let me know. If you have done this calculation, let me know the answer, please. So we have minus QD, and then what is the results? What is the result that you got from this integration? So if I do the differentiation of 1 over r squared plus b squared to the power half, then we are going to get so the power is minus half 1 over r squared plus b squared to the power 3 over 2. Then we have r squared here, so it is 2r is equal to minus 1 over minus r over r squared plus b squared to the power 3 over 2. So with this result, I have minus here, so it will be positive here. So this is the function that we needed to integrate. So if I differentiate this function, then I'm getting this function. So if I integrate this function, I should get this function here. So for this integration, you will get minus 1 over r squared plus b squared to the power half. Now the total charge is equal to QD over limit is going from 0 to infinity r squared plus b squared square root, and the limits are 0 to infinity. So if I apply infinity to r, this term will be 0, but when I apply 0 to this term, so we have minus qd over d squared to the square root, so we have d. So d cancels out. Final answer will be minus q. So now for this situation, now for this method of images discussion, first we initially had this Q charge here, then I introduced negative charge here, and then we calculated what is the potential at this point P due to this plus Q and minus Q, and then we assume if there is a a conducting plane on this xy plane. So if xy plane is a conducting plane, then we calculated due to this potential, what is the charge density that will be generated. So if xy plane is a conducting plane, due to this potential, what is the charge density that will be induced, that will be generated. And then for the charge density, for the charge distribution, we obtained this equation, and with that one, on this xy plane, there will be a negative q charge induced on this xy plane. Okay. Now with those two, like mainly the potential, mainly we have three results: the potential and this charge density and the total charge. So we mainly have the potential, charge density, and the total charge. So let's see whether our assumption is correct. So we assumed xy plane is a conducting plane, and that is also grounded. Grounded means potential is 0 on this xy plane. So potential should be 0 on the xy plane. Now, so with this potential on this xy plane, when z is equal to 0, when z is equal to 0, here we will have q over x squared plus y squared plus d squared minus q over x squared plus y squared plus d squared square root. So these two terms will be cancelled out. The total potential on this xy plane will be 0. So our first calculation for the potential will, it is act like xy plane is a grounded conducting plane where the potential is 0. So when xy plane is considered, z is equal to 0, and when z is equal to 0, we have q over x squared plus y squared plus d squared square root minus q over x squared plus y squared plus d squared square root. So these two terms will cancel out. The potential will be 0. Therefore, in this situation, this xy plane will act like a grounded conducting plane because of the potential here. And with this initial condition we considered plus q, there is a, so initially there is plus q, then we introduced minus q, and because of this plus q mainly, we have a charge density, charge distribution on this xy plane that will change like this. So with x and y, the charge density will change. Also with the d distance, charge density will change. And then the final result we obtained, the total charge that will be induced in this situation is equal to minus q. Therefore, so if we have a grounded conducting plane, in this case, xy plane, and when we have a charge q here, then to solve that situation, what we can do is we can add a charge like here, charge minus q here with the same distance from the plane to solve, to simplify a question where we have one charge here and the conducting plane. Okay, so that is the method of images. So now initially the question we discussed, suppose a point charge is held at a distance d about an infinite grounded conducting plane like this. So in this situation, we don't know, it will be a little bit hard to calculate the potential since we don't know how much charge is induced and how it is distributed. So to solve a situation like this, what we can do is we can introduce another charge that have the same magnitude but opposite in sign. So if I have a plus q here, then I'm going to introduce a minus q, and with the same distance from the grounded conducting plane. So with that introduced charge, it is the same situation like this grounded conducting plane. So when I introduce the minus q charge here, then I can ignore this grounded conducting plane and do the calculation. So it is the same. Mathematically, we showed that it is the same situation. Now, the same uh, calculations that I did are given in these slides. So first, to solve this situation, suppose a point charge is held at a distance d above an infinite grounded conducting plane. So we ignore this grounded conducting plane and we introduce a minus q charge here. Then with that minus q charge, we calculated what is the potential due to both of these charges plus q and minus q. So this is the potential. And then if I assume that we have xy plane, a conducting plane with this potential, the calculated potential will be 0. So it is going to be act like a grounded conducting plane. And then, so these results we discussed during our discussion about conductors. When we place a conductor in an electric field, we discuss these results, these ones. And then using those results, we calculate the charge density. So charge density is going to distribute like this. Then with the charge density, we calculate the total charge that is induced by the these two, mainly these due to these two plus q and minus q charges. And the total charge we obtained, we calculated that is equal to minus q. So when we have a plus q here, then due to this grounded conducting plane, on this grounded conducting plane, there will be a negative charge induced on this grounded conducting plane. So that is what we have calculated here. So this method is not limited to a single point charge. Any stationary charge distribution near a grounding conducting plane can be treated in the same way by introducing mirror images. So initially we have this plus q charge, then we introduce an image of the charge with the opposite sign. So when we have a plus q, we introduce the minus q charge. Now, so any questions from this method of images? Method of images Any questions? So you will it will be clear for you a little bit more when we do a question. So try this question. Now in this question, there is a grounded conductor. So this xy plane is a grounded conductor, and we have two charges here. First charge is at a distance 3d from the origin, and that charge magnitude of that charge is plus q. Then we have another charge from origin to that charge. The distance is d, and the magnitude is minus 2q. So find the force on the charge q if xy plane is a grounded conductor. So if this xy plane is a grounded conductor and we have these two charges initially, these two charges are there. So calculate the force on the charge, this plus q, due to this minus 2q and due to this grounded conductor. So try this one. And if you have any questions, you can ask or you can type in the chat. Please do so. Now here we have XY plane. It is a grounded conductor. So which means potential here is 0. And we have Z direction. And here we have plus Q. And here we have minus 2Q. Distance here is D. And distance here is 2D. So we need to calculate force on charge plus Q. Now, what we learn from this method of images, if when we have a grounded conducting plane, so by introducing images of these charges, so I have here minus 2Q, so I will introduce plus 2Q. Then here I have plus Q, then I will introduce minus Q with the same distance. So these are the images of the initial charges. So when I introduce these images, those images and these original charges will induce it will act like it will be equal to the situation where we have a grounded conductor. Okay, so when we introduce these image charges, it is the same situation. Mathematically we showed that when we have a grounded conductor, there are certain amount of charges induced on this conductor. So that amount of induced charges and this method of images are mathematically the same. So when we have a grounded conducting plane and charges like this, then we can introduce these images. So it is mathematically the same as we have a grounded conducting plane here. Okay. Then we just need to calculate the force due to three of these charges on this plus Q. So force can be calculated 1045 epsilon naught Q and Q r squared in the direction of r. So let's say our plus Q is capital Q is this plus Q. So we have 1045 epsilon naught with this Q. First I will consider this minus 2Q and the separation between these two is 2D squared. Then we have Q with this plus Q and this plus 2Q. The separation is, now we have 3D here and 1D, so 4D squared. Then with this minus Q and this plus Q, plus Q minus Q. Now the separation is 6D. And the direction will be in the Z direction. So if you do the simplification for this one, you can get the answer. So we have 1/4 epsilon naught Q squared. Here it is 1 minus 1/4. Here it is plus 2/16. And here it is minus 1/36. Direction is same. And you can get the final answer. It should be this answer. Minus 1 over 4 pi epsilon naught 29 q squared over 72 d squared in the direction of z. Check whether you are getting this answer.